Let's talk about slipping on ice. You've done it, right? You step out on a frozen sidewalk, your foot goes flying, and suddenly you're doing an involuntary split or landing hard on your backside. Or maybe you've watched ice skating, those graceful glides across the rink, the effortless turns, the way skaters seem to float. And then there's curling, where they're sliding heavy stones across ice like it's nothing. So you've seen it, you've experienced it. Ice is slippery. That's just obvious. Everyone knows that. So you must understand it, right? You understand why ice is slippery. Okay, explain it to me. What actually happens at the molecular level when your shoe touches ice? Why does frozen water behave so differently from, say, frozen concrete or frozen wood? Those things get cold and hard, but they don't become slippery. What makes ice special? Here's the thing. Most people can't actually explain it. They might mumble something about smoothness, or they've heard something about melting, but they don't really know. And what's more interesting, the explanation you've probably heard, it's wrong. For over a century, scientists told a simple story. They said ice is slippery because of something called pressure melting. The idea goes like this. When you step on ice, your weight creates pressure. That pressure lowers the melting point of the ice right where you're standing. So a thin layer of water forms between your shoe and the ice, and that water acts like a lubricant. You're essentially skating on a microscopic water layer that your own weight created. Sounds reasonable, doesn't it? This explanation was taught in textbooks. It was repeated by teachers. It became common knowledge, and it has a nice intuitive feel to it. Pressure does something, ice melts, slippery happens. Case closed. Except here's the problem. The physics doesn't work. Think about it. How much pressure do you actually create when you stand on ice? Or better yet, think about an ice skater. An ice skater might weigh, say, 60 kilograms, and that weight is concentrated on those thin blades that create significant pressure, right? But do the calculation. That pressure would lower the melting point of ice by maybe a fraction of a degree, maybe. And that only works if the ice is already close to melting temperature, near 0 degrees Celsius. But ice is slippery at minus 10 degrees, at minus 20 degrees, at minus 30 degrees. People skate in outdoor rinks in Canada at minus 20, and the ice is still slippery. The pressure melting explanation completely fails here. So if pressure melting doesn't explain it, what does? To understand this, we need to ask better questions. We need to stop accepting simple answers and start digging into what's really happening. First question, what does it even mean for something to be slippery? When you say a surface is slippery, you're really saying there's very little friction between your shoe and that surface. Friction is the force that resists motion when two surfaces are in contact. High friction means things stick like rubber on dry pavement. Low friction means things slide easily like your shoe on ice. So the real question is, why is there so little friction between objects and ice? Second question, what's special about the surface of ice? Ice isn't just frozen water sitting there like a solid block of rock. Ice is water molecules arranged in a crystalline structure, locked into place by hydrogen bonds. But here's what's crucial. The ice at the surface, the very top layer of molecules, isn't in the same environment as the ice beneath it. The molecules in the bulk of the ice are surrounded on all sides by other water molecules. But the molecules at the surface, they're exposed to air on one side. They have neighbors missing, and that changes everything about how they behave. Third question, what happens at the surface of ice even when nothing is touching it? This is the key. This is where the real physics lives. Even when ice is just sitting there, alone, untouched, at minus 10 degrees or minus 20 degrees, something strange is happening at its surface. The surface molecules aren't quite solid and aren't quite liquid. They're in a weird in-between state. Scientists call this a quasi-liquid layer. It's not liquid water as you'd pour from a glass. It's not solid ice as you'd chip from a block. It's something in between, a molecularly thin layer where the water molecules are mobile, disordered, able to flow past each other, even though the temperature is well below freezing. This layer exists on ice regardless of pressure, regardless of whether anything is touching it. It's just there, all the time on every ice surface exposed to air. This is what makes ice slippery. Now let's understand why this quasi-liquid layer exists. This gets to the heart of how molecules behave, and it's beautiful. Think about a water molecule inside a block of ice. It's surrounded by other water molecules in all directions, above, below, left, right, front, back. Each of those neighboring molecules pulls on it through hydrogen bonding. These hydrogen bonds are like little springs connecting the molecules, holding them in that rigid crystalline structure we call ice. The molecule is trapped, locked in place by all those bonds pulling from every direction. That's what makes ice solid. Now think about a water molecule at the surface of the ice. It's got neighbors below it pulling it down. It's got neighbors to the sides pulling it sideways. But above, nothing. There's just air. And air molecules don't form hydrogen bonds with water molecules the way other water molecules do. So this surface molecule is missing neighbors. It's missing bonds. It has fewer constraints. And here's what that means. The surface molecule has higher energy. In physics, we talk about surface energy, the extra energy that surface molecules have compared to molecules in the bulk. Why higher energy? Because those missing bonds represent unrealized attractions, unsatisfied connections. The molecule wants to bond with something above it, but there's nothing there. That makes it energetically frustrated, unstable. When molecules are energetically frustrated, they do something to relieve that frustration. And for water molecules at the ice surface, the way they relieve it is by becoming more mobile. They start to wiggle more. They start to move more freely. They break away from the strict crystalline order of the ice beneath them. They enter this quasi-liquid state, not fully liquid, because they're still partially connected to the ice structure below, but not fully solid either, because they're mobile and disordered. This isn't melting in the normal sense. Melting would require you to add heat energy to break all the bonds throughout the ice. This is different. This is a spontaneous surface phenomenon driven by the fact that surface molecules are in a different environment than bulk molecules. It happens even at temperatures far below the normal melting point. And here's the crucial part. This quasi-liquid layer is incredibly thin. We're talking nanometers, billionths of a meter, maybe 10 to 100 molecules thick, depending on the temperature. At very cold temperatures, like minus 30 degrees, it might be just a few molecules thick. As you get closer to 0 degrees, it gets thicker. But it's always there. This layer has been measured. Scientists have used techniques like spectroscopy and atomic force microscopy to probe the surface of ice at various temperatures. They've confirmed it. There's a disordered, mobile layer on ice surfaces. It's real, it's measurable, and it's the reason ice is slippery. So now you understand there's a quasi-liquid layer on ice. But why does that make ice slippery? What's the connection between this mobile surface layer and the lack of friction you feel? Friction between two surfaces depends on how well those surfaces can grip each other. When you walk on concrete, the microscopic roughness of your shoe sole interlocks with the microscopic roughness of the concrete. There are contact points, adhesion forces, mechanical interlocking. All of that creates resistance to motion. That's friction. But when you step on ice, your shoe doesn't contact the solid ice directly. Instead, it contacts this quasi-liquid layer, and that layer behaves very differently. Think about what a liquid does. Liquid molecules can flow. They can slide past each other. They don't have fixed positions. When your shoe presses down on that quasi-liquid layer, the molecules in that layer don't interlock with your shoe. They just move out of the way. They flow. They rearrange themselves to accommodate the pressure without creating strong adhesion or mechanical resistance. It's like the difference between pressing your hand into sand versus pressing your hand into water. Sand grains are solid. They pile up. They interlock. They resist your motion. Water just flows around your hand. The quasi-liquid layer on ice is more like the water. But here's an important subtlety. The quasi-liquid layer isn't just sitting there passively. When you apply pressure, when you step on it, when a skate blade presses down, you do create a bit more disorder in that layer. You do enhance its liquid-like character slightly. The pressure doesn't melt the solid ice beneath in any significant way, but it does interact with the quasi-liquid layer that's already there, making it even more mobile, even more fluid. So there's a dynamic interaction happening, The quasi-liquid layer exists independently, but when you apply pressure and motion, you're also shearing that layer. You're forcing it to flow. And because it's already in a mobile, disordered state, it flows easily. That easy flow is what we experience as slipperiness. Temperature matters too. At very cold temperatures, the quasi-liquid layer is thinner and less mobile. There's less of it to act as a lubricant. That's why ice actually becomes less slippery at extremely cold temperatures. If you've ever walked on ice at minus 30 degrees versus minus 5 degrees, you might have noticed this. The colder ice has more grip. Not a lot, but noticeably more. That's because the quasi-liquid layer is thinner and behaves more solid-like. As the temperature rises towards zero, the quasi-liquid layer gets thicker and more liquid-like. The ice becomes more slippery. And once you actually reach 0 degrees and start truly melting the bulk ice, you get full liquid water on the surface, and the slipperiness increases even more. So it's all about this layer, this beautiful, weird, in-between state of matter that exists at the boundary. This quasi-liquid layer on ice isn't just an isolated curiosity. It's an example of a fundamental principle in physics. Surfaces are different from bulk. Everywhere in nature, the surface of a material behaves differently than the interior. Why? Because symmetry is broken at the surface. Inside a material, every atom or molecule is surrounded by similar neighbors in all directions. There's symmetry, balance. But at the surface, that symmetry is broken. There are neighbors missing on one side. And that broken symmetry changes the energy, changes the bonding, changes the behavior. This shows up everywhere. The surface atoms of metals vibrate differently than interior atoms. The electrons at the surface of a semiconductor behave differently than electrons in the bulk. That's why surface states are so important in electronics. The molecules at the surface of a liquid have different energy than molecules in the bulk. That's what creates surface tension. And for ice, the broken symmetry at the surface creates this quasi-liquid layer. It's not an exception. It's an example of a universal principle. Here's another deep point. This phenomenon tells us something about phase transitions. We usually think of phase transitions as sharp water is liquid above 0 degrees and solid below 0 degrees. But that's only true in the bulk. At surfaces and interfaces, phase transitions are smeared out. There are intermediate states. The quasi-liquid layer on ice is a surface phase that exists below the bulk melting point. It's neither liquid nor solid in the traditional sense. This kind of thinking, recognizing that surfaces, interfaces, and boundaries have special physics, is essential in modern science. It matters in materials science, where surface properties determine how materials corrode, how they catalyze reactions, how they stick to other materials. It matters in biology, where the behavior of membranes and protein surfaces determines the function of cells. It matters in nanotechnology, where you're often working with materials so small that most of their atoms are on the surface. And it all comes back to the same principle. Symmetry breaking at boundaries creates new behavior. So when you're slipping on ice, you're not just experiencing a simple consequence of ice is smooth or pressure makes it melt. You're experiencing a consequence of fundamental thermodynamics and statistical mechanics. You're experiencing what happens when surface molecules, freed from some of their bonds, spontaneously enter a partially disordered state to minimize their free energy. That's what Feynman would want you to understand. Not just the surface explanation, not just there's a layer, but why the layer exists, what principles govern it, and how it connects to broader ideas in physics. Because once you understand the principles, you don't just understand ice, you understand a way of thinking about matter, surfaces, and phase transitions that applies everywhere. Here's the thing that should blow your mind. You've been experiencing quantum mechanics and statistical physics every time you've slipped on ice, and you didn't even know it. That quasi-liquid layer, it exists because of the statistical behavior of enormous numbers of molecules governed by quantum mechanical bonding. Those hydrogen bonds holding ice together are quantum mechanical entities. They're not little springs. They're shared protons existing in quantum superpositions between oxygen atoms. The energy landscape that determines whether a molecule stays crystalline or becomes mobile is fundamentally quantum. And the decision of whether the surface molecules are ordered or disordered, that's statistical mechanics. It's about free energy minimization. At any given temperature, nature is doing a calculation. Is the system's total free energy lower if the surface molecules are locked in a crystal or if they're mobile and disordered? The answer depends on the balance between energy and entropy. At the surface, where bonds are missing, the entropy gained from disorder outweighs the energy cost, and the quasi-liquid layer forms. So every time you ice skate, you're gliding on a nanometer-thin layer of water molecules that are in a partially disordered state because quantum mechanics and thermodynamics favor that state at the boundary between ice and air. Nature is doing high-level physics at every frozen pond, and we just walk across it without thinking. And here's the final twist. Scientists argued about why ice is slippery for over 100 years. The pressure melting explanation seemed obvious, seemed intuitive, but it was wrong. The truth required sophisticated surface science and careful experiments to reveal. Sometimes the obvious explanation is wrong. Sometimes you have to look deeper, question harder, and accept that reality is stranger and more beautiful than your first guess. So what's the lesson here? The lesson is that the world doesn't owe you simple explanations. The universe is under no obligation to be easy to understand. Ice is slippery not because of some straightforward mechanical reason you can grasp in 5 seconds, but because of subtle surface thermodynamics and the statistical behavior of molecules in broken symmetry environments. And that's wonderful. That's what makes physics beautiful. You start with a simple question, why is ice slippery? And you end up learning about surface energy, phase transitions, hydrogen bonding, and the fundamental difference between bulk and boundary. Every ordinary phenomenon, when you interrogate it deeply enough, opens up into something profound. So next time you see ice, don't just think slippery. Think about those surface molecules wiggling in their quasi-liquid state. Think about the broken symmetry. Think about the free energy minimization happening at the nanoscale. And ask yourself, what other everyday things do I think I understand but actually don't? Because that's where the real learning begins. That's where curiosity lives. That's where you start thinking like a physicist.